Welcome. In this lesson, you will learn about the AIMSIM multi-domain and multi-level capability and the value it brings. In AIMSIM, we work on the energy flow basis. On the screen, you see an electric motor attached to a mechanical rotary shaft. Electrical domain is represented in purple color, whereas mechanical domain is represented in green. The rotary shaft drives a hydraulic pump modeled in blue. Mechanical gearbox is connected to a compressor which is part of pneumatics domain as seen in a different color. So in AIMSIM, we work with all these different domains seamlessly. The user doesn't have to worry about the intricate details, and it is a matter of picking the right physics to build an AIMSIM model. The first example we looked was a relatively simple model. Now what you see is a more complex model of a hybrid vehicle thermal management system, where you have everything modeled from an engine cooling system to an engine thermal masses as well as the electrical network for the vehicle. We have an electrical motor connected to the drivetrain that goes out and actually drives the vehicle. Gasoline engine is used to charge the battery, controller for the vehicle, powertrain controller, etc. So you can go from a very simple multi-domain to a very complex model that defines the dynamics of a system as complex as hybrid vehicle. Besides handling multi-domains like signals and controls, mechanical, hydraulics, thermal, electrical, we can also link it to the other commonly used solutions. For example, in the mechanical domain, we can connect to the finite element analysis for doing structural analysis or multi-body simulation for doing full vehicle responses on engines and vehicles. In the hydraulics domain, a common application will be to use CFD to calculate the jet forces around the spool valve and integrate those results into the AIMSIM model to get more accurate performance prediction from the AIMSIM model. Now, what is multi-level nature of SimCenter AIMSIM? Since AIMSIM is a system-level platform, you can move from multi-domain to multi-level. When you initially build your model, you have the option of creating a very detailed physical model or a functional model which characterizes the performance of that component model. What we have on the screen are the different levels that you can model a check valve. In the functional model, an user defines the parameters that defines the performance of this model. For example, what pressure the valve is supposed to crack open and what is the flow gradient, and no details are provided in terms of the size of the spring, number of coils, the mass of the component and valves. Just the simple performance related functional parameters are required. As the design evolves, it might become necessary to model more of the physics for a check valve, so the user might take an element approach and use the hydraulic component design library to include more physics into the model. For example, the functional model will be replaced by a physical model that will include details of the mass of the moving components, the stiffness, damping of the spring, performance of the poppet valve, volume, size of the orifice, and things like that. These details can be modeled to model the physics of the check valve as well as using the so-called block diagram. One has the opportunity to use mathematical approach to the modeling. For example, using the signal and control library, the user can create equations that represent the flow rate and the pressure drop of the particular valve and model that valve with those kinds of components. In addition, there is a programming level where you can use C or Fortran or even Modelica to write equations that characterizes the performance of your given model. So these are the four different type of levels that an engineer can use to model a check valve. This ends our lesson on multi-domain and multi-level capabilities of SimCenter AIMSIM.